Nothing in this room is actually still. The walls, the floor, the air inside it are all moving faster than any commercial jet in the sky right now. Physicists settled this more than a century ago, and most people have never heard the actual answer. Your chair is moving at 1,670 kilometers an hour, just from the spin of the planet. The Earth itself is carrying you around the Sun at 107,000 kilometers an hour, and the Sun is dragging the entire Earth through the galaxy at 828,000 kilometers an hour. Tonight, we'll climb through 6 different layers of motion, each one faster and stranger than the last. We'll reach the one number physicists treat as the closest thing to a true speed for our galaxy. We'll find out why even that number carries a hidden problem nobody has ever fully solved. And by the end, you'll understand exactly why the question, "How fast are you moving?" has never had a single correct answer. If this is the kind of night you return to, it helps this quiet universe keep growing. Let's begin. Put your palm flat against the nearest wall. It feels solid. It feels like the one fixed thing in the room. It is moving at 1,670 kilometers an hour. And so is the floor under your feet. And so are you. That number belongs to the planet's spin, measured at the equator, slower the farther you sit from it. Still fast enough, wherever you are tonight, to outrun the cruising speed of almost anything with wings. Not once since you were born has your body dropped below that speed. Not while you slept through 100 ordinary nights. Not during the stillest minute of the quietest afternoon you can remember. What makes that number strange isn't its size. It's that you cannot feel a single kilometer of it. No wind presses against your skin. No hum rattles the glass in the window. The spin that carries you is smoother than the smoothest highway you've ever ridden. Smoother than it has any right to be, given the number attached to it. Scientists have a simple explanation for why. You, the air, the walls, and the water in your glass are all spinning together, locked to the same rotating floor, so nothing in the room has any speed relative to anything else inside it. Motion without friction is motion you cannot sense. That is the trick, and it is not a small one. You've spent every night of your life turning gently through that same loop, without once waking up dizzy. A jet cruising at 900 kilometers an hour already feels indistinguishable from stillness to the passengers strapped inside it, coffee sitting undisturbed on the tray table. And that jet is moving at barely half the speed the ground itself is already carrying you. Scale that same absence of sensation up by nearly double, and you have the rotation of the entire planet, running underneath every ordinary afternoon you have ever spent doing nothing in particular. But the trick has a part that unsettles it rather than explaining it away. Whatever direction you happen to be facing right now, you are not simply spinning in place like a coin balanced on a table. Every point on this rotating planet is being carried in an enormous circle around an axis, and stand at the equator and you complete a full circle of just over 40,000 kilometers every single day, day after day, without a pause, without so much as a break for the days spent doing nothing at all. 40,000 kilometers in one day, every day. And the odd part isn't the size of that circle. The odd part is what happens the moment you try to name the center it circles around. The axis running through the poles isn't anchored to anything outside the planet. It's anchored to the planet itself, which is why the question of what, exactly, you're spinning relative to has a far less comfortable answer than the ground. Because the ground is spinning too, which leaves exactly one candidate solid enough to check your speed against. The star sitting a familiar, comfortable 93 million miles away, the one you've been taught since childhood to picture as the anchor of everything else. Surely that one holds still. The sun does hold still, relative to the spin under your feet. That much is true. And it has been true for as long as anyone alive has been counting days. But holding still was never really the claim. The Earth is not parked near a stationary star the way a boat sits tied off at a dock. It is falling around that star continuously at something close to 107,000 kilometers an hour, fast enough to cross the distance between New York and London in under 2 minutes, sustained without a single pause, for all 365 days it takes to complete one loop. Falling is the accurate word here, not floating. Released from that orbit, the planet would not drift gently away into open space. It would fall in a straight line, the way anything falls when nothing bends its path into a curve. What holds Earth to a curve instead of a straight line is the sun's gravity, pulling at every instant, correcting the fall into a circle wide enough that it never actually lands. An orbit isn't the absence of falling, it's falling that keeps missing. Physicists have a blunt way of making the same point concrete. Cut the cable holding an elevator car mid-shaft, and for the handful of seconds before it hits anything, everyone inside floats free of the floor, weightless, because the car and its passengers are falling at exactly the same rate. Nothing pins them to the floor anymore, because nothing needs to. The Earth's fall around the Sun works on that identical principle, just stretched over the courtesy of a very large radius and a very patient gravity, so that the 1,000 small warnings a snapped cable would give you never arrive at all. You have never felt that fall tilt the floor, and you never will, for the same reason you never felt the planet spin everything around you. The walls, the water, the air in the room falls at exactly the rate you do. There is no relative motion inside a falling room, only outside it. Astronauts learn to live inside that exact fact. A person can hover motionless in a falling spacecraft, papers scattered around them also hovering, because falling together erases the sensation of falling entirely. You have been running a slower, gentler version of that trick every day since before you could walk. Here's the detail: almost nobody sits with long enough to feel its full weight. Every position on the circle Earth is falling through gets visited exactly once. The precise location in space you occupied on your last birthday, not the date, the location itself, is a point this planet will never pass through again. Not next year, not in any year left to the solar system. The Sun is not standing still enough to let the Earth retrace an old lap around a fixed center, and neither, it turns out, is anything else nearby, which raises a question that should have been settled by now and hasn't been. If the Sun isn't a fixed point either, the circle the Earth traces isn't a circle stitched onto stillness. It's a curve stitched onto some larger motion. And that motion, once you find it, makes everything counted so far look almost stationary by comparison. Here is the number that makes the first two disappear. The Sun, carrying Earth and every other planet along with it, is moving through the Milky Way at roughly 828,000 kilometers an hour. Not around a star this time, around the entire galaxy. A spiral of several 100 billion other stars, all orbiting a common center the way planets orbit a sun, except at a scale that swallows the comparison whole. Fold that speed into time instead of distance, and something else falls out. One full circuit of that galactic orbit takes something close to 230 million years. Astronomers have a name for it, a galactic year. And by that clock, the solar system has completed only about 20 of them since it formed. 20 laps. In the entire history of the Sunday, scale that single planetary year down to one ordinary heartbeat. And the mismatch gets sharper still. Fold the 230 million years of a single galactic year down to that same scale, and you get something close to 6 years of continuous heartbeats, day and night, waking and sleeping, without a single pause. Just to represent one complete lap of the orbit, the solar system is already partway through. Tonight, whether your own heart happens to be racing or resting, sit with what fits inside a single one of those laps. The last time the solar system stood at this exact point in its galactic orbit, continents on Earth were still fused into a single landmass, and nothing resembling a dinosaur had yet walked across any part of it. An entire branch of life, origin, rise, and extinction, fits inside one loop around the galactic center, with room left over. You will not complete even a fraction of a percent of this orbit in your lifetime. Neither will anyone whose name you know. Neither, almost certainly, will the species itself. And unlike Earth's yearly loop around the Sun, this one doesn't trace a neat closed circle either. The Sun bobs gently above and below the galactic plane as it travels, drifting through the thin disk of the Milky Way like a needle rising and dipping through fabric. A slow vertical drift layered on top of the horizontal one, adding a wobble scientists still can't fully explain to a path already too vast to feel. Estimates put that vertical bob at somewhere between 2 and 3 full crossings of the galactic disk per orbit. A slow rise and fall on a rhythm measured in tens of millions of years per swing. So, the ground spins, the Sun falls, and drags the ground with it. The Sun itself is caught in something almost 230 million years wide, wobbling as it goes. 3 separate motions, 3 separate speeds, and every one of them checks out under the math. A galaxy isn't a fixed stage that the Sun crosses the way a train crosses a bridge. The stage itself is moving. The Milky Way is not sitting still while the Sun orbits inside it. The entire galaxy, every star, every planet, every one of those 230 million years is itself being pulled across space, towards something astronomers can describe far more precisely than they can explain. In the 1970s and 1980s, teams of astronomers mapping the motion of nearby galaxies noticed something that shouldn't have been there. Thousands of galaxies, scattered across an enormous region of sky, all appeared to be drifting in the same general direction. Not randomly, the way you'd expect from ordinary cosmic traffic, but coherently, like water beginning to circle a drain that hadn't been located yet. Something massive, hidden well beyond the Milky Way, was pulling on all of it at once. They called it the Great Attractor, and the name has outlived every attempt to replace it with something more precise. Estimates place its pull equivalent to tens of thousands of times the mass of our entire galaxy, concentrated roughly 250 million light-years away. And for decades, nobody could look directly at it. The Great Attractor sits behind the flat disk of the Milky Way itself, in a region so choked with our own galaxy's stars, gas, and dust that astronomers still call it the zone of avoidance. We are being pulled, measurably, towards something we cannot point a telescope at without our own galaxy blocking the view. For comparison, the Milky Way itself, the galaxy holding every star you have ever pointed at and named, carries a mass equivalent to a few 100 billion suns. Whatever sits at the center of the Great Attractor's pull outweighs that comparison so thoroughly that our entire galaxy becomes one thread among many, gathered as part of something with no name, simple enough yet to replace the placeholder. Astronomers gave it decades ago. This isn't a small nudge, and the scale of it should sit uncomfortably. The local group, the modest cluster of galaxies that includes the Milky Way, Andromeda, and a few dozen smaller companions, is being drawn toward that hidden mass at roughly 600 kilometers every second. Convert that, and you get a figure larger than every speed named so far tonight combined. Something in the neighborhood of 2 million kilometers an hour, layered underneath the spin, underneath the orbit, underneath the galactic wobble, all at once. None of it announces itself. There's no lurch, no sensation, nothing to mark the moment the Great Attractor's pull was discovered versus the moment before anyone knew to look for it. Only the measurement was new. So now the tally includes a galaxy being hauled sideways by something it has never directly seen, at a speed that outpaces the Sun's own orbit within that galaxy. And the very fact that we needed a decades-long survey just to notice something this large moving this fast should tell you something about how much of this motion is designed to stay invisible from the inside. Which leaves an uncomfortable follow-up question nobody answered in the 1980s. and nobody has fully answered since. If something we can't see is strong enough to move an entire galaxy, what, if anything, is pulling on that? For most of the 20th century, the Great Attractor was as far as the map went. Astronomers knew something massive was out there, pulling galaxies toward it. They did not know what it belonged to, or how big the structure containing it actually was. That changed only recently. Recently enough that many people reading a science headline about it today are older than the discovery itself. In 2014, a team led by astronomer Brent Tully published the first map of the full supercluster surrounding the Milky Way, using the motions of tens of thousands of galaxies to trace the boundary of a structure nobody had previously outlined. They named it Laniakea, a Hawaiian word meaning immense heaven, and it turned out to be almost incomprehensibly large, roughly 500 million light-years across, containing something on the order of 100,000 galaxies, of which our own is one undistinguished member drifting somewhere near the outer edge. Laniakea isn't held together the way a solar system or even a single galaxy is held together. There's no central object anchoring it, the way the sun anchors its planets. It's defined instead by flow, by the shared direction every galaxy inside its boundary is drifting, all converging, eventually, toward the gravitational basin that includes the Great Attractor. Step outside that boundary, cross into a neighboring supercluster's territory, and the galaxies there are drifting toward an entirely different basin instead. The universe, at this scale, behaves less like a set of objects and more like a landscape of watersheds, and the Milky Way happens to sit inside one particular basin's collection area. Picture rainfall landing across an enormous stretch of land, none of it falling in a single spot, all of it eventually finding its way toward the same low valley, simply because gravity gives it nowhere else to go. Laniakea works on that same logic, just written in gravity instead of water, over a span of 500 million light-years instead of a single watershed. The galaxies inside it aren't being pulled by one object so much as they're all sliding downhill together, toward the same gravitational low point at rates too small to notice within any single human lifetime, but too consistent across 100,000 galaxies to be coincidence. Here's the fact that deserves a second look before moving past it. Humanity had already split the atom, walked on the moon, and mapped the human genome before anyone had confirmed the name, shape, and boundary of the very supercluster we live inside. We had detailed models of atomic nuclei decades before we had a map of our own cosmic neighborhood. That gap between what we can measure up close and what we still don't know at the largest scales is not a footnote. It's close to the actual shape of the problem. Because even Laniakea's slow 500 million light-year drift toward its own gravitational basin isn't the final word on how fast we're moving. Some of what astronomers have found moving through this landscape doesn't drift toward Laniakea's basin at all. It moves towards something else, and nobody has yet worked out a convincing reason why. In the early 2000s, a team of astronomers analyzing the motion of hundreds of distant galaxy clusters noticed something that didn't fit the standard picture of large-scale flow. The clusters weren't just being tugged around by nearby structures like the Great Attractor or the broader Laniakea Basin. A subset of them appeared to share a small, consistent, leftover motion, after every known local pull had been subtracted from the math, all pointing in roughly the same direction, toward a region of sky near the constellations Centaurus and Hydra. They called it dark flow. The team that first flagged it, led by astrophysicist Alexander Kashlinsky in 2008, measured the effect using something called the kinematic Sunyaev-Zeldovich effect, a subtle distortion galaxy clusters imprint on the cosmic microwave background as they move through it, separate from the dipole caused by our own motion. After stacking data from hundreds of clusters to cancel out noise, the same faint residual drift kept surfacing. Clusters moving at somewhere between 200 and 1,000 kilometers a second toward that one patch of southern sky. a range wide enough to reflect real uncertainty in the measurement, but narrow enough that a directional trend, rather than random scatter, kept reappearing. Nobody has a settled explanation. One proposal treats it as an artifact of the measurement technique itself, the equipment or the method, quietly producing a false signal. A more unsettling proposal treats it as real, a faint pull from something that exists entirely outside the observable universe, beyond the boundary of everything light has had time to reach us from. A structure so large its gravity leaks across a horizon that light itself cannot cross. And only that leak reaches us. Neither camp has won the argument. The data has been reanalyzed more than once, using better instruments and larger galaxy cluster catalogues, and the finding is still debated in the literature rather than settled by it. Cited by some teams as confirmed, contested by others as noise, with no consensus paper closing the case in either direction. What began as a puzzling anomaly in the early 2000s remains. Right now, tonight, exactly that. There is something genuinely odd about how open this question still is. We can date the age of light that has been traveling since almost the beginning of time. We can measure the mass of galaxy clusters hundreds of millions of light years away with real precision, and we still cannot say, with full confidence, whether a portion of the visible universe is drifting towards something we will never be able to see directly, because it sits past the one boundary nothing gets to cross. If dark flow turns out to be real, the implication is almost too large to hold comfortably. Some of what we call the observable universe would be gently, measurably responding to a companion piece of universe it can never observe back. We'll leave that exactly where the astronomers have left it, unresolved, sitting quietly under everything else moving tonight, waiting for an answer nobody currently has. In 1964, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna to study radio waves from the Milky Way. Every time they pointed the antenna at the sky, in every direction, at every hour of the day and every season of the year, they picked up a faint, constant hiss of microwave static they could not get rid of. They assumed it was equipment error. They checked the wiring. They checked the receiver. At one point, they climbed into the horn antenna itself and physically scraped out a layer of what they described, with some understatement, as white dielectric material, droppings left by a pair of pigeons that had been nesting inside the instrument. They cleaned it thoroughly. The hiss remained, identical in strength, coming from every direction, day and night, summer and winter, with no variation traceable to the antenna, the city, or the season. What Penzias and Wilson had stumbled onto, without initially realizing it, was the faint afterglow of the Big Bang itself. Light released roughly 380,000 years after the universe began. When it first cooled enough to become transparent, stretched by billions of years of cosmic expansion, until it arrived at their antenna not as light at all, but as microwave static. Physicists elsewhere had predicted this radiation should exist years earlier, but nobody had detected it until two engineers trying to clean bird mess off an antenna picked up the oldest light in the observable universe by accident. Only a short drive away, at Princeton, a team led by physicist Robert Dicker was already building an antenna specifically designed to search for this same afterglow, working from predictions made as early as 1948. When Dickey's team heard what Penzias and Wilson had accidentally found, the two groups published side by side in 1965. One paper announcing the discovery, the other explaining what it meant. Dick is said to have turned to his colleagues after the phone call and said simply, "Well, boys, we've been scooped." A prediction nearly 2 decades old, and a deliberate search already underway, both beaten to the finish line by an antenna full of pigeon droppings. What matters more than the discovery story itself is this: the faint hiss doesn't come from any one direction. It doesn't come from a source you could point a more powerful telescope at and get a sharper image of. It comes from everywhere, uniformly, because it was released everywhere at once back when the entire universe was still hot and dense enough to glow. Every patch of empty sky you could aim an antenna at carries a piece of that same ancient glow, cooled now to a few degrees above absolute zero, the quietest kind of light there is. That uniform, ancient hiss did something no earlier discovery on this list managed to do. It gave astronomers something to measure our motion against. That isn't another galaxy, another cluster, or another supercluster drifting on its own. It's the afterglow of the event that started everything drifting in the first place. And it turns out that afterglow isn't quite as uniform as Penzias and Wilson first assumed. If the light left over from the Big Bang were perfectly uniform in every direction, it would prove one specific thing. Whoever measured it wasn't moving relative to the material that released it. That isn't what satellites measuring this ancient glow actually found. Missions including COBE, WMAP, and Planck, mapping this radiation with increasing precision from the late 1980s through the 2010 seconds, all found the same subtle pattern. The glow is very slightly warmer in one direction and very slightly cooler in the opposite direction, differing by only a few thousandths of a degree, invisible to any instrument less sensitive than these. That tiny asymmetry has a name, the CMB dipole, and it has a cause simpler than the size of the discovery suggests. It looks exactly like the pattern you'd expect if you were moving through the glow rather than sitting still inside it. The same way a windshield gathers more raindrops on its front than its back, the faster a car drives through the rain. Run the math on that tiny temperature difference, and a number falls out. Our galaxy, our local group, the whole gravitationally bound neighborhood we belong to, is moving at roughly 630 kilometers every second. Relative to this ancient light, something close to 2,250,000 kilometers an hour, once you convert it into units that mean something to a body sitting in a chair, faster than the sun's own orbit around the galactic center, faster than the pull toward the Great Attractor alone would explain. Once you account for it as only one ingredient in the total, this particular number gets treated differently from every other one named tonight, for a reason that isn't obvious at first. The rotation of the Earth is measured against the Earth itself. The sun's orbit is measured against the galaxy. The galaxy's drift is measured against the Great Attractor, and the Great Attractor's position is measured against still larger structures. Every measurement so far has been relative to something else that is also moving. The cosmic microwave background is different. It fills the entire observable universe uniformly, left over from a single moment shared by everything that exists, which makes it the closest thing physicists have to a fixed backdrop for the whole of space. 630 kilometers a second against the oldest light there is. For a long moment, that looks like the answer we came here for. A true speed, at last, measured against something bigger than any local structure. Bigger than any single galaxy's private drift. It's the number NASA's own mission pages use when they need to describe how fast the Milky Way is really moving. But the closest thing physicists have to a fixed backdrop is a very specific, very careful phrase. And it is not the same claim as the fixed backdrop. That difference is about to matter more than anything counted so far. Strip away the story of Penzias, Wilson, and the pigeons for a moment, and look only at the measurement itself, because the measurement is where the real claim lives. The cosmic microwave background has an average temperature of 2.725 Kelvin, just a few degrees above absolute zero, uniform across the sky, to a precision that took 3 generations of satellites to actually confirm. But uniform was never quite true. Layered on top of that, near-perfect evenness is a much smaller pattern. One broad region of sky reads very slightly warmer than the average, and the region exactly opposite it reads very slightly cooler by roughly the same tiny amount. The difference is on the order of a few thousandths of a Kelvin. a fraction so small that ground-based instruments in the 1960s and 1970s couldn't reliably detect it at all. This pattern is called the dipole, and it isn't distributed randomly across the sky the way instrument noise would be. It has a clean, simple geometry. One pole hot, the opposite pole cold, and a smooth gradient connecting them. Exactly the shape you'd expect from a single cause rather than many scattered ones. That single cause is relative motion. An observer moving through a uniform bath of radiation measures it as compressed and therefore hotter in the direction of travel, and stretched, therefore cooler, in the direction left behind. It's the same Doppler principle used to measure the speed of receding galaxies, applied here to the faint microwave glow instead of visible starlight. Measure the size of the hot to cold gradient precisely enough, and the observer's velocity relative to that glow falls directly out of the math. No separate assumption required. The dipole itself was first detected in 1977 using a U-2 spy plane modified to carry microwave detectors above most of the atmosphere's interference in an experiment led by physicist George Smoot. Years before COBE turned the same measurement into one of the most cited results in modern cosmology. 3 space missions confirmed the same dipole independently, using 3 different instruments built a decade or more apart. COBE in the early 1990s, WMAP through the 2000s, and Planck through the 2010 seconds. Each one refining the number rather than contradicting it. The dipole corresponds to a velocity of approximately 369 kilometers per second in one specific direction, toward a point in the constellation Leo, which, once combined with the separately measured motion of the Sun around the galactic center and the galaxy's own motion within the local group, produces the combined figure of around 630 kilometers per second for the entire local group's motion relative to the cosmic microwave background as a whole. None of this measurement requires knowing what caused the Big Bang, or what existed before it, or why the universe expanded the way it did. It requires only 2 things: an extremely sensitive thermometer and a sky large enough to compare one half against the other. That is the entire method. A hot side, a cold side, a number that falls out of the gap between them. In 1887, in a basement laboratory in Cleveland, Ohio, physicists Albert Michelson and Edward Morley built one of the most sensitive instruments of their era for a single purpose: to detect the wind. Not ordinary wind. At the time, physicists assumed that light, like every other wave they knew of, needed some physical medium to travel through, a substance filling all of space, invisible and weightless, that they called the luminiferous ether. If the ether existed and held still while the Earth moved through it, then the planet's own orbital motion, roughly 30 kilometers a second, should create something like a headwind pressing against light traveling in one direction and a tailwind assisting it in the other. The way running through still air changes how fast the air seems to move past your face. Michelson and Morley built an instrument precise enough to catch that difference, a device called an interferometer, splitting a single beam of light into 2 perpendicular paths, bouncing each off mirrors and recombining them to look for the tiniest possible mismatch in arrival time. If Earth were plowing through a stationary ether, the beam traveling with the wind and the beam traveling against it should return microscopically out of step, producing a visible shift in the interference pattern where the 2 beams met. They floated the entire device on a pool of mercury to eliminate vibration, rotated it slowly through every possible orientation, and repeated the measurement across different times of day and different seasons to rule out the possibility that they had simply aimed it in the one direction where the wind happened to cancel out. The shift never appeared. Not a partial shift. Not a smaller than expected shift requiring a more sensitive instrument. No shift at all, at any orientation, at any time of year, to a precision far finer than the effect they had built the machine specifically to catch. For nearly 2 decades afterward, Physicists proposed increasingly elaborate patches to save the ether, objects dragging a thin shell of it along as they moved, or physically contracting in the direction of motion by an amount that exactly disguised the wind from any instrument built to detect it. Both explanations technically fit the data. Neither explained why nature would bother hiding a wind so completely, using a coincidence precise enough to fool every experiment anyone could design. One young physicist, working as a patent clerk in Switzerland and largely outside the mainstream of academic physics at the time, proposed something stranger and far simpler than either patch. There was no wind to hide, because there was no ether for the Earth to move through in the first place. Light didn't need a medium. It didn't need a favored frame of reference at all. And once he followed that idea all the way through, the entire architecture of space, time, and speed came apart and reassembled into something almost nobody in 1905 was prepared for. Albert Einstein didn't set out to explain the null result from that basement in Cleveland. By his own account, years later, he arrived at his conclusions more from thinking through the physics of electricity and magnetism than from Michelson and Morley's data specifically. But the two lines of reasoning pointed at exactly the same door. And in 1905, Einstein walked through it. His starting assumption was almost insultingly simple, stated as two rules, rather than an elaborate new mechanism. First, the laws of physics look identical to every observer moving at a constant velocity, no matter what that velocity is, with no experiment able to distinguish truly still from moving smoothly from the inside of a sealed room. Second, and far stranger, the speed of light in a vacuum is the same for every one of those observers, regardless of how fast they themselves are moving, or in what direction, or how fast the source of the light is moving. That second rule sounds like a technicality until you work out exactly what it demands. Fire a beam of light from a ship moving at half the speed of light, and a stationary observer watching from a dock does not measure that beam arriving at 1.5 times light speed, the way you'd expect if you added the ship's speed to the beam's speed, the ordinary way velocities add. Both the ship's crew and the observer on the dock measure the exact same speed for that beam. Something else has to give to make that true. And what gives, Einstein showed, is the very things that seemed most fixed. The rate at which time passes and the length of the ship itself, both becoming dependent on how fast something is moving relative to whoever is doing the measuring. Fold that all the way out and a much larger consequence falls loose. If two observers moving at different constant speeds each get to call themselves at rest, with equal justification, if neither one's laws of physics behave any differently and neither one's light beam behaves any differently, then the entire question of who is really moving and who is really still stops being a question physics can answer at all. There is no cosmic scoreboard checking everyone's speed against a hidden zero. There is only ever speed measured relative to something else you chose to measure it against. That single idea, tested and confirmed for well over a century now, in laboratories, particle accelerators, and satellite clocks, is the quiet foundation sitting underneath every number counted so far tonight. The spin of the Earth, the fall around the Sunday, the drift toward the Great Attractor. Every one of those speeds was only ever a comparison, this relative to that, dressed up to sound like a fact standing on its own, which means the 630 kilometers a second measured against the oldest light in the universe isn't exempt from that rule either. It's a comparison too. A very good one, just not on its own the exception Einstein's physics would allow. Picture two spacecraft passing each other in deep space, far from any planet, any star, any reference point either crew could point to and call the ground. Each ship's instruments read the same, engines off, cabin steady, nothing pressing anyone back into their seat. From inside either ship, the other one appears to be moving, and their own ship appears to be standing still. Ask the crew of the first ship how fast they are going, and the honest, complete answer is not a number. It's a question in return. Going relative to what? Relative to the second ship, they are moving at whatever combined speed separates the two hulls. Relative to a star system neither ship has visited yet, they are moving at some entirely different number. Relative to the light from a galaxy on the far side of the observable universe, different again. None of those numbers is more true than the others. None of them is the ship's real speed, held in reserve behind the others like an answer key. Give the two ships actual numbers, and the discomfort gets sharper rather than softer. Ship 1 clocks, Ship 2 moving away at 80,000 kilometers per second. Ship 2, using instruments just as accurate, clocks Ship 1 moving away at exactly the same 80,000 kilometers per second in the opposite direction. Both measurements are complete. Both instruments are functioning correctly, and there is no third measurement taken from some perfectly neutral position that would settle which ship actually did the moving. There is no neutral position. There never was one to stand in, and no upgrade to either ship's instruments, no matter how sensitive or expensive, would ever locate one. This is the part that resists being comforted away, and rushing past it would miss the point entirely. It is not that we have failed, so far, to measure a hidden true velocity underneath all the relative ones. It is that Einstein's physics rules out the existence of that hidden number entirely on principle, not as a temporary gap in instrumentation waiting for a better telescope. Two crews, passing each other at any speed you like, both get to be right that they are the ones holding still. Not one of them is secretly wrong, waiting to be corrected by someone with better data. Extend that same logic to every number named so far tonight, and something almost dizzying falls out of it. The Earth's spin, the fall around the Sun, the drift toward the Great Attractor, the 630 kilometers a second against the ancient light. None of them is your true speed being slowly uncovered, layer by layer. Each one is a separate, equally valid comparison, and there is no final layer where the comparisons stop and the real number appears. If that unsettles something, it is meant to. Sit inside it a moment before we keep moving. Long before Einstein, before Michelson and Morley ever floated their instrument on a pool of mercury, a much older thought experiment had already reached the same uncomfortable conclusion, using nothing more advanced than a sailing ship and a jar of butterflies. In 1632, the astronomer Galileo Galilei published an argument in defense of a moving Earth, a position that had already gotten him in serious trouble with the church of his time. Critics of a moving Earth had a common objection. If the planet were really hurtling through space, shouldn't we feel it? Shouldn't a ball dropped from a tower land slightly behind where it was released, since the ground beneath it had kept moving while the ball fell? Galileo's answer took the form of a thought experiment rather than a telescope. Imagine yourself sealed below the deck of a large ship, he wrote, with no window to the outside. Drop objects. Watch fish. Swim in a bowl of water. Throw something to a friend across the cabin, and every one of those actions behaves exactly the same whether the ship sits motionless in harbour or glides smoothly across a calm sea at a steady speed. No jolt, no lag, no dropped object landing behind where it was released. As long as the ship's motion stays smooth and constant, nothing happening inside that sealed cabin can tell you whether the ship is moving or still. That single argument, worked out 3.5 centuries before satellites or particle accelerators existed to confirm it, already contained the seed of everything measured tonight. Galileo used it to answer critics of a moving Earth. It turns out to answer a far larger question too. Not just whether the Earth moves, but whether moving and still were ever absolute categories to begin with, rather than categories that only make sense once you specify moving relative to what. You are that sealed cabin right now. No window shows you the spin of the planet beneath the room, or the fall around the sun, or the drift toward a hidden mass millions of light years away. Every object in the room with you, the water in your glass, the air pressing evenly against your skin, the walls holding their shape around you, moves at exactly the speed you do For exactly the same reason the fish in Galileo's bowl never noticed the ship. You have been living inside that argument since before you could read it. 390 years after he first wrote it down, for people who thought the idea itself was heresy. Einstein later gave this principle a name of its own, Galilean relativity, and built his own 1905 breakthrough as a direct extension of it, changing only one assumption Galileo had taken for granted, that time and space themselves stayed the same for every observer, no matter their speed. Drop that single assumption, keep everything else, Galileo argued, and special relativity is what falls out the other side. Suppose for a moment that you wanted to actually stop, not slow down, stop completely, relative to everything else in the universe at once. The request runs into trouble almost immediately because everything else isn't moving together. Cancel your speed relative to the room around you, and you're still spinning with the planet. Cancel the planet's spin, and you're still falling around the Sunday. Cancel that fall, and you're still being carried through the galaxy at the sun's orbital speed. Cancel that, and the entire galaxy is still sliding toward the Great Attractor, itself part of a supercluster, sliding toward its own gravitational basin, which may itself be answering to something even larger that nobody has finished mapping. Each of those motions points in its own direction, at its own speed, answering to its own local cause. There is no single maneuver, no combination of engines firing in exactly the right sequence that could cancel all of them out simultaneously, because cancelling your motion relative to one thing generally means gaining motion relative to another. Match the average galaxy's drift, and you'd be moving hard relative to the Sunday. Match the sun, and you'd be falling relative to the galaxy's center. The universe does not offer a single direction whose cancellation buys you stillness relative to all the others at once, because the universe itself is not moving in a single direction. Run the numbers on just 2 of tonight's layers, and the trap becomes concrete. Cancel the Earth's spin by traveling exactly opposite the planet's rotation at 1,670 kilometers an hour, and relative to the ground, you would finally be still. But relative to the sun, depending on the moment and the angle, that same cancelling motion can add directly onto the planet's much larger orbital speed instead of subtracting from it. Solve for stillness against the ground, and you can actively worsen your case against the Sunday. There is no version of this arithmetic that lets you win against every layer using the same move, and adding a third layer, then a fourth, only multiplies the number of ways the trade can work against you. True stillness, the kind that would satisfy every one of those comparisons simultaneously, would require the universe to hold still relative to itself first. It doesn't. Galaxies drift apart from each other. Clusters fall toward other clusters. Even the ancient light left over from the Big Bang is expanding, stretching, cooling as it goes. Asking to be still relative to all of it at once is asking a moving river to hold one part of itself in place while the rest keeps flowing past. So the stillness you feel right now, sitting wherever you're sitting, it was always just an agreement, unspoken, unfelt, and entirely local, between you and the small patch of universe closest to your skin. Every galaxy beyond our own local group is retreating from us. That much has been established since the 1920s, when astronomer Edwin Hubble first measured the redshift of dozens of distant galaxies and found a pattern. The farther away a galaxy sat, the faster it appeared to be rushing away. In almost every direction he checked, space itself, it turned out, was expanding, carrying galaxies apart the way marks drawn on the surface of a balloon spread apart as the balloon inflates, with no galaxy actually launching itself through space toward anywhere. That expansion, called the Hubble flow, is not the same thing as any of the motions counted so far tonight. It isn't a galaxy drifting toward a Great Attractor or falling into a supercluster's gravitational basin. It's the space between galaxies stretching, a completely different mechanism producing a similar looking result, redshifted light, and an appearance of retreat. Here's where it stops being simple. Every galaxy has both kinds of motion layered on top of each other at once. The smooth, predictable retreat caused by cosmic expansion, and a separate, local drift caused by ordinary gravity, the same kind of pull tugging our own galaxy toward the Great Attractor. Astronomers call that second component peculiar velocity, and for any single galaxy, especially a distant one, separating the two signals apart is genuinely difficult. A galaxy's total observed redshift is the sum of both effects added together, and only the nearest, best measured galaxies allow astronomers to confidently tease the local drift apart from the cosmic stretch underneath it. Andromeda is the clearest nearby example of how completely peculiar velocity can override the larger expansion. At only 2.5 million light-years away, close enough that cosmic expansion barely registers, Andromeda's own gravitational pull toward the Milky Way dominates the numbers completely, producing a blue shift instead of a red shift. The one large nearby galaxy where the local drift wins outright over the retreat the expansion alone would otherwise produce. Move far enough away, though, and that balance flips, quietly and gradually, until the expansion's redshift swallows the local drift almost completely, hiding it inside a number that looks, from here, like simple retreat. For most of the galaxies visible in even the deepest images ever taken, that separation has never been fully done. We know, in general terms, that peculiar velocities exist everywhere, layered under the larger expansion, nudging every galaxy sideways by some amount relative to the smooth retreat the expansion alone would produce. We do not have a complete map of exactly how much of any single distant galaxy's motion belongs to which cause, which means somewhere in every deep field image ever captured, galaxies are drifting sideways for reasons never fully untangled from the reasons they're also rushing away. Both stories are true of the same light, arriving at the same telescope on the same night. Nobody has finished separating them out. Nobody, tonight, is going to. Every speed counted so far tonight needed something to be measured against. The planet's spin needed the ground. The sun's pull needed the planet. The Great Attractor's pull needed a map of galaxies drifting together. Even the 630 kilometers a second, measured against the cosmic microwave background, needed that ancient light to exist as a backdrop first. Light itself breaks that pattern, and it is the only thing known to break it. Measure the speed of a beam of light from a laboratory sitting still on Earth, and you get exactly the same number, 299,792 kilometers a second, that you would get measuring the same beam from a spacecraft moving at a meaningful fraction of that speed in the same direction the light is traveling, or the opposite direction, or any direction at all. Ordinary velocities add and subtract depending on who's measuring and from where. Light's speed does neither. It arrives at the same number for every observer, regardless of how fast that observer happens to be moving relative to anything else. That single exception is not a loophole in the rule that every speed is relative. It's closer to the reason the rule exists at all. Einstein didn't discover that everything is relative and light simply follows along. He discovered that light speed is the one fixed point the entire universe agrees on, and relativity, the fact that every other velocity depends entirely on what you compare it to, is the direct, unavoidable consequence of holding that one thing fixed, which makes light the strangest object in tonight's entire account. Every planet, star, galaxy, and supercluster named so far has a speed that depends on your point of view. Light is the sole exception, the one entry on the list that would return the same number no matter which of tonight's moving platforms you happen to be standing on when you measured it. The spinning ground, the falling Earth, the orbiting sun, the drifting galaxy, all of it. Stand on any of them, measure the same beam of light, and get the identical answer every time. Push any object with mass fast enough, and this same fixed point starts pressing back in a way nothing else in the universe does. The closer an object's speed creeps toward light's, the more energy it takes to add even a small amount more, not because of some engineering limit still waiting for a smarter design, But because the mathematics of relativity treats light speed as a boundary, nothing with mass can ever fully reach, only approach, more and more expensively, forever falling just short. Photons get to travel at that speed only because they carry no mass to begin with. Anything that does, from the smallest dust grain to a body sitting still in a chair, is permanently, structurally barred from joining them at the one speed the entire universe agrees on. If light speed has to stay fixed for every observer, something else has to bend to make that promise possible. What bends, it turns out, is time itself. In 1971, physicists Joseph Hafele and Richard Keating tested this directly, using nothing more exotic than commercial airliners and 4 cesium atomic clocks, precise enough to notice differences of a few billionths of a second. They flew the clocks around the world twice, once eastward and once westward, while an identical set of reference clocks stayed on the ground at the U.S. Naval Observatory. When the travelling clocks landed and were compared against the stationary ones, they didn't agree. The clocks that had flown eastward, moving with the Earth's rotation, ran slightly behind the ground clocks. The clocks that had flown westward, moving against the planet's rotation, ran slightly ahead. The differences were tiny, measured in tens of billionths of a second, but they matched the predictions of relativity almost exactly. Neither set of clocks was broken. Neither reading was the correct one, with the other simply drifting out of calibration. Each clock had genuinely experienced a different amount of time because each had moved through space at a genuinely different speed relative to the others. And time itself, according to relativity, runs at a rate that depends on relative motion rather than ticking forward at one universal pace for everyone. The same effect shows up in nature without any airplane involved. Muons, unstable subatomic particles created when cosmic rays strike the upper atmosphere, decay so quickly that, by ordinary accounting, almost none of them should survive the trip down to the Earth's surface. And yet detectors on the ground register them by the billions every day. Moving at a large fraction of the speed of light, those muons experience far less time passing from their own reference frame than a stationary observer on the ground would calculate for the same journey, enough less that many of them arrive intact, having effectively borrowed extra time from the very act of moving fast enough to need it. A debt physicists can measure to the microsecond in any particle detector on Earth on any given afternoon without needing a single airplane ticket. Fold that into everything counted so far tonight, and the discomfort compounds. Not only does your speed depend entirely on what you compare it to, the amount of time passing for you, right now, in this room, technically depends on it too, by an amount too small to notice at the speeds a human body ordinarily reaches, but real, measured, and confirmed by clocks precise enough to catch it. You are not just moving at several different valid speeds simultaneously. You are, in some vanishingly small but entirely real sense, experiencing time itself at a slightly different rate than someone moving differently than you are, right now, reading or listening to these same words from somewhere else in that same shared, restless universe. In a short popular book on relativity published in 1917, Einstein offered a scenario simple enough to picture without any equipment at all. A long train moving at a steady, ordinary speed, and 2 bolts of lightning striking the track at the same instant. One near the front of the train and one near the back. A person standing on the embankment, exactly halfway between the 2 strike points, sees both flashes of light arrive at the same moment. For that observer, the 2 lightning strikes are simultaneous, by any reasonable definition of the word. A passenger sitting exactly in the middle of the moving train, at the precise instant the 2 bolts struck, does not see them arrive at the same moment. Because the train is moving toward the front strike and away from the back one, the passenger meets the light from the front strike slightly sooner, and the light from the back strike slightly later. From inside the train, the front lightning strike happened first. This holds even after every signal delay has been carefully subtracted out. It would be easy to assume the passenger simply perceived the front strike first because the light from it had less distance left to travel by the time the train had moved partway there, a straightforward consequence of finite light speed rather than anything deeper. Relativity's claim survives that correction entirely. Once every delay caused by the light's travel time is properly accounted for, the disagreement about which strike came first does not go away. It's not an illusion produced by uneven signal arrival. It's a genuine disagreement about the sequence of the two events themselves, built into the geometry of space and time, and not removable by better instruments or more careful bookkeeping. Neither observer's account is a trick of perception, correctable with better eyesight or a faster reaction time. Both measurements are complete. Both instruments would confirm what each observer reports, and both are describing the same two physical events. The order in which those two events occurred is not a fixed fact about the universe, waiting to be measured correctly by someone with a better vantage point. It genuinely depends on how fast the observer is moving relative to the events themselves. Stretch that same effect across cosmic distances instead of a train platform, and the discomfort compounds rather than fading. Two events separated by enough distance and little enough time between them, a flare on one star and a flare on another, can occur in one order for an observer moving one way and the opposite order for an observer moving another way, with neither observer wrong and no further measurement capable of settling which flare really came first. This is not a claim about how information travels, or about delays caused by the time light takes to arrive. It survives every one of those corrections already built in. It is a claim about the deeper structure of time itself, that at the same time, and even before and after, were never universal facts stamped onto events independent of who was watching and how fast they were moving when they did. Point at Polaris tonight, and you are pointing at true north, the one star that appears to hold still while every other star in the sky wheels slowly around it over the course of a night. That fact has been true for only a small slice of human history, and it will stop being true again, slowly, on a schedule so old it was first noticed using nothing more than careful record-keeping roughly 21 centuries ago. The Greek astronomer Hipparchus, comparing his own star catalogue to observations recorded centuries earlier, I noticed that the positions of the stars relative to the equinoxes had shifted by an amount too large and too consistent to be observational error. He couldn't explain the mechanism, but he correctly identified the pattern. The entire sky appears to slowly rotate around a second, much larger circle, completing one full turn only after tens of thousands of years. The actual cause, worked out centuries later, is a wobble in the Earth's own axis. The same kind of slow tilt a spinning top develops as it loses speed, except Earth's version is driven by the gravitational tug of the sun and moon on the planet's equatorial bulge, rather than friction and fatigue. The axis itself traces a large, slow circle in the sky over a period of approximately 26,000 years, dragging the position of true north along with it. Polaris happens to sit closest to the north celestial pole right now, in the thin slice of that 26,000-year cycle that includes recorded human civilization. It was not the pole star when the pyramids at Giza were built. A much dimmer star, Thuban, held that position instead. It will not be the pole star roughly 12,000 years from now, when the axis will have swung far enough that the bright star Vega takes over the role instead, visible to anyone who thinks to look up and check. Some of the entrance shafts inside the Great Pyramid at Giza are believed by some archaeoastronomers to have been aligned toward Thuban specifically, built to frame the pole star of that particular era rather than the one visible tonight. Modern star charts carry the same problem in miniature. Professional catalogues are published for a specific reference epoch, commonly labelled something like J2000, and have to be periodically reissued precisely because the slow wobble keeps nudging every star's apparent position, decade after decade, away from where the previous chart said it would be. Fold this into everything already counted. The ground spins daily. The Earth falls yearly around the Sunday. The Sun drags everything through a 230 million year galactic year. And underneath even the daily spin, the axis of that spin is itself slowly tracing its own much slower circle, changing which star gets to call itself true north on a timescale long enough to outlast entire branches of the family tree that eventually became you. Every layer, once you look closely enough, turns out to be wobbling inside a slower layer still. In the 1960s, astronomer Vera Rubin wanted to measure something that sounded almost mundane: how fast stars orbit at different distances from the center of a spiral galaxy. Getting the chance to make that measurement at all had already required clearing an obstacle that had nothing to do with astrophysics. Rubin was repeatedly denied formal access to major observatories earlier in her career, simply because she was a woman. When she finally became, in 1965, the first woman granted official observing privileges at the Palomar Observatory in California, the facility didn't even have a women's restroom, and Rubin is said to have solved the problem herself by taping a paper skirt to the men's room sign on the door. Rubin died in 2016 without ever receiving a Nobel Prize for the discovery that followed, an omission many physicists still describe as one of the award's more conspicuous oversights. Working alongside instrument maker Kent Ford, Rubin turned her attention to the Andromeda Galaxy and dozens of other spirals, measuring the orbital speed of stars and gas clouds at increasing distances from each galaxy's center. The expectation, based on the visible distribution of stars and gas alone, was straightforward. Stars near the crowded, mass-heavy center should orbit fast, and stars out in the sparse, nearly empty outer reaches should orbit much slower, the same way planets farther from the Sun move more slowly than planets close in. That is not what Rubin and Ford found. Stars far out at the edges of these galaxies, in regions with barely any visible matter left to hold them in place, were orbiting just as fast as stars much closer to the crowded center. By every calculation using only the mass visible through a telescope, disks moving that fast at their edges should have flown apart entirely, flinging stars out into open space over the course of only a few galactic rotations. They hadn't flown apart, which meant something was holding those outer stars in their orbits. Something contributing enormous amounts of gravitational pull without emitting or reflecting any light a telescope could detect. Rubin and Ford's rotation curves, confirmed and extended across dozens more galaxies through the 1970s and 1980s, became some of the strongest evidence for what astronomers now call dark matter, an invisible form of mass, outweighing all the visible stars and gas in a typical galaxy by a factor of roughly 5 to 1, wrapped around galaxies like the Milky Way in a halo far larger than the visible disk itself. That single measurement changes what every number counted so far tonight actually means. The Sun's own orbital speed around the galactic center, 828,000 kilometers an hour, is only correct because it accounts for the pull of a halo of matter nobody has ever directly seen. Rubin measured the effect of something she could never observe directly, using nothing more than the stubborn, measurable behavior of ordinary starlight refusing to slow down where the math said it should. Every motion counted so far has measured the Sun against something large: the galaxy's center, the Great Attractor, the cosmic microwave background. There's a smaller, stranger motion hiding underneath those, measured against something much closer: the ordinary stars sitting nearest to us, the ones visible without a telescope on any clear night. Average out the motion of the stars in the Sun's immediate neighborhood, close enough that their combined average roughly cancels out the larger galactic orbit shared by all of them. And something is left over. The Sun is not sitting still relative to that local average either. It's drifting away from it, at roughly 20 kilometers a second, toward a specific point in the sky astronomers call the solar apex, located near the border of the constellation Hercules, not far from the bright star Vega. The direction itself isn't a modern discovery. William Herschel, the astronomer who discovered Uranus, first calculated an approximate direction for the Sun's motion through the local star field in 1783 using nothing more than the catalogued positions of a handful of bright stars. And the assumption that their observed drift across the sky partly reflected the sun's own movement rather than theirs alone. His estimate, worked out entirely by hand more than 2 centuries before satellites could measure stellar positions to fractions of an arcsecond, placed the solar apex in roughly the same region of sky. Modern surveys still confirm today. Nobody fully agrees on the cause. Some of that drift may simply reflect the sun's particular position within its slow vertical bob through the galactic disk, described earlier. Some may reflect the ordinary gravitational jostling any star experiences drifting among billions of neighbors, each pulling gently on the others over millions of years. What's not in question is the measurement itself. Relative to the average of the stars around us, the sun is heading somewhere steadily and has been for as long as anyone has had instruments precise enough to notice. There's a detail here that deserves more than a passing glance. This motion is invisible from the ground in a way the others aren't even in principle. You cannot watch the stars near Hercules grow slowly brighter over a human lifetime. The drift is too slow, the distance is too vast, for any unaided eye across any single human life to register the difference. The sun could carry the entire solar system toward that patch of sky for 10,000 years running. And the night sky above your house would look, to you, essentially unchanged the whole time. So even the local sky, the stars you can point to and name, is not a fixed backdrop the sun sits still against. It's simply moving slowly enough, relative to a human lifetime. That stillness is the only thing anyone alive has ever had the chance to notice. Generation after generation, long before anyone had a name for the apex it was quietly heading toward, astronomers needed a convenient reference point for measuring motion within the sun's immediate neighborhood. So they built one. It's called the Local Standard of Rest. And the name makes it sound like a place, a fixed marker anchored somewhere in the galaxy the way a survey stake is driven into ground. It isn't. The Local Standard of Rest is an average, the mean motion of a large sample of stars in the sun's general vicinity, smoothed out to cancel the small individual wanderings of any one star among its neighbors. Nothing physically sits at that averaged velocity. No star, no cloud of gas, no object of any kind actually travels at exactly the Local Standard of Rest's precise speed, because it was never a measurement of anything real to begin with. It was a convenience, invented to give astronomers a working 0 point sturdy enough to measure the sun's 20 km/s drift against. There's a further complication that rarely makes it into introductory explanations. Astronomers actually use 2 different definitions of the Local Standard of Rest, depending on the calculation at hand. One based on averaging the motion of nearby stars directly, the kinematic version, and another based on a theoretical model of how stars would move in a perfectly smooth, symmetric galaxy, the dynamical version. The two don't quite agree with each other. Depending on which definition a given research paper adopts, the sun's measured drift relative to its surroundings shifts by a small but real amount. Not because the sun's actual motion changed, but because the reference point being measured against was itself a slightly different fiction. An invented average, built from a fiction that comes in 2 competing versions, sitting underneath a measurement that already sits underneath a dozen larger ones. Nobody treats this as a flaw in the science. It's simply what a local standard always was. Not a place, not an object, not anything the universe itself recognizes. A tool, useful exactly as long as everyone agrees to pretend it's real. Every average behaves this way. Once you look closely enough, ask for the average height of everyone in a room, and no single person in that room needs to be exactly that height for the average to be real and useful. The Local Standard of Rest works the same way, at a much larger scale. Real enough to calculate with, useful enough to build entire research careers around, and still, at bottom, a number describing no actual object drifting through the galaxy at that exact velocity. That gap between useful and real turns out to run through nearly every reference point named tonight so far. The Great Attractor's exact center, the boundary of Laniakea, the precise value of the Hubble constant, which different measurement techniques still return slightly different answers for, decades after the number was first estimated. Science doesn't need a reference point to be a real, solid object sitting somewhere in space. It only needs the reference point to be consistent enough and agreed upon widely enough for the resulting measurements to mean the same thing to everyone using them. The Milky Way's own disk, dense with stars, gas, and dust, blocks roughly 1/5 of the entire extragalactic sky from direct optical observation. Astronomers call that band the zone of avoidance, and for most of the 20th century, it functioned as a permanent blind spot, a stripe across the sky where entire galaxies, clusters, even superclusters, could sit completely undetected, hidden behind the light and dust of our own home galaxy. In 2016, an international team led by astronomer René Kraan-Korteweg announced the discovery of a massive concentration of galaxies sitting almost directly behind that blind spot, using radio and near-infrared surveys capable of seeing through the dust that blocks ordinary visible light. They named it the Vela supercluster, and early estimates place its total mass in a range that could rival some of the largest known structures already mapped in the more visible parts of the sky. Early estimates suggest the Vela supercluster's total mass could reach somewhere in the range of hundreds of thousands of times the mass of the Milky Way, a scale that would place it among the more significant structures influencing the deep sky flow patterns astronomers have spent decades trying to map. Confirming numbers that large requires more than one survey. The Vela detection combined redshift measurements from optical telescopes able to peek through the thinner edges of the dust with entirely independent radio observations, which pass through galactic dust largely unaffected, cross-checking one method against the other patiently across several years of follow-up observation before the team was willing to publish a discovery of that size. The timing itself is the strange part. This was not a distant, early discovery from the primitive years of the field. It was announced in the same decade that produced fully mapped human genomes, functioning quantum computers, and spacecraft actively operating past the edge of the solar system. An entire supercluster, potentially massive enough to influence the motion of everything discussed so far tonight, sat unnoticed behind our own galaxy's disk until a research team specifically built the tools to look through the one place nobody had properly checked. Nobody yet knows exactly how much the Vela supercluster's gravity contributes to the local group's overall drift, layered in alongside the Great Attractor and the broader Laniakea flow. The measurements are recent, the mass estimates still carry real uncertainty, and untangling one hidden structure's pull from another's, when both sit partially behind the same obscuring band of dust, is exactly the kind of problem that takes decades to fully resolve rather than years. What's certain already is smaller and stranger than any specific number. The map of what's pulling on us has not been finished. It may never be finished, not because the effort has stalled, but because our own galaxy sits directly in the way of 1/5 of the sky we would need to check completely clear, permanently, for as long as we remain inside it. For years after its discovery, the Great Attractor looked like an endpoint, the single hidden mass finally responsible for the sideways drift of the entire local group. Later surveys complicated that picture considerably. Mapping the region beyond the Great Attractor, astronomers found that the flow of galaxies doesn't stop at the Great Attractor's location. It continues past it, toward an even more massive structure, sitting roughly 650 million light-years away. The Shapley concentration, one of the largest known superclusters in the observable universe, containing thousands of galaxies bound into a structure so massive that some researchers now treat the Great Attractor less as a final destination and more as a way station, a regional clump caught in the pull of something considerably larger, still sitting farther along the same line of sight. The relationship between the two isn't fully settled. Some analyses suggest the Great Attractor's own gravity accounts for most of the local group's sideways drift on its own, with the Shapley concentration adding only a smaller, secondary tug layered on top. Others suggest the reverse. that the Shapley concentration's sheer mass, at that scale, plays the dominant role, with the Great Attractor itself being pulled toward Shapley the same way our own local group is being pulled toward the Great Attractor. Either way, the structure doesn't end where the name once implied it would. The Great Attractor attracted an entire generation of astronomers into treating it as the answer. The mass at the bottom of the gravitational basin, the place all the falling finally stops. It isn't the bottom, it's a step, sitting partway down a slope that continues past it, toward a supercluster whose own eventual boundary nobody has finished mapping either. The scale involved is difficult to hold in the mind for long. The Shapley concentration alone is estimated to contain a mass equivalent to roughly 10 million billion suns spread across thousands of individual galaxies bound into a single gravitationally significant structure, one of the largest such concentrations identified anywhere in the mapped universe. For comparison, the entire local group, our home patch of roughly several dozen galaxies including the Milky Way and Andromeda, amounts to a rounding error against a structure that size. And there is no obvious reason to assume Shapley itself sits at the bottom of anything. Large-scale structure surveys mapping the distribution of galaxies across billions of light-years consistently find the same pattern repeating at every scale checked so far. Clusters gathered into superclusters, superclusters gathered into still larger filaments and walls, with no confirmed larger structure yet identified as the final one. Whether that pattern eventually bottoms out somewhere or simply continues past the current limits of what telescopes can measure remains one of the open questions in modern cosmology, not a solved one. Every hidden mass discovered so far tonight has turned out to be falling towards some larger hidden mass in turn. Nothing counted yet has been the flaw. Every speed counted so far tonight has come with its own number. 1,670 kilometers an hour for the planet's spin, 107,000 for the orbit around the Sun, 828,000 for the journey around the galaxy, 630 kilometers a second against the cosmic microwave background. Add them together in the ordinary way, arithmetic adds numbers, and you'd get an enormous, precise-sounding total. That total would also be wrong. Speed, in physics, is only part of the actual quantity that matters. The complete quantity is velocity. Speed combined with a specific direction, and direction is exactly the piece plane addition throws away. Two velocities pointing in the same direction do add together in something close to the simple way. Two velocities pointing in opposite directions partially cancel. Two velocities pointing at an angle to each other combine into something in between. Calculated with the same geometry used to combine any two arrows pointing in different directions, not with the simple arithmetic used to combine two plane numbers. Here's a concrete version of the problem. At one moment during the planet's daily spin, your local motion from that spin points in roughly the same direction as the Earth's orbital motion around the Sun, and the two speeds add close to fully. 12 hours later, the planet's rotation has carried you to the opposite side of the Earth, and your local spin motion now points closer to the opposite direction from the orbital motion, subtracting from it instead. Your actual combined speed relative to the Sun genuinely rises and falls slightly over the course of a single day, purely from the changing angle between two motions that never themselves change size. Spacecraft engineers deal with this exact problem every time they plan a real mission. Sending a probe to another planet isn't a matter of pointing at where that planet will be and firing thrusters at some single combined escape speed. Every maneuver has to account for the spacecraft's velocity relative to Earth, Earth's velocity relative to the Sun, and the destination planet's own velocity relative to the Sun, all as separate vectors, combined and recombined at each stage of the trip. Get the direction of any one of those velocities slightly wrong, and the probe misses its target by a margin that no amount of raw thrust can fix after the fact. Layer in the Sun's motion around the galaxy. The galaxies drift toward the Great Attractor, and the whole local group's motion against the cosmic microwave background, each pointing in its own separate direction, and the total figure that would represent Your actual combined speed through space isn't a fixed number waiting to be calculated correctly. It changes constantly, shifting by the hour, by the day, by the season, as each layer's direction rotates relative to the others. There was never a single number to add up to. There were only ever arrows, pointing in different directions, occasionally lining up and occasionally cancelling, never once resolving into the one true figure the question seems to be asking for. Your heart, resting quietly right now, beats somewhere around once a second. It has kept a version of that rhythm since before you were born, sped by exertion, slowed by rest, but never straying far from that same 1 second neighborhood for your entire life. Space itself keeps a completely different kind of rhythm, one with no beats at all, just a steady, continuous stretching. Astronomers measure that stretching using a number called the Hubble constant, currently estimated at somewhere close to 70 kilometers per second for every 3.3 million light-years of distance separating 2 points in space. A galaxy sitting that far away recedes from us at roughly 70 kilometers a second, purely from the expansion of space between here and there. A galaxy twice as far recedes at roughly twice that speed. The relationship holds, roughly, all the way out toward the edge of the observable universe. A single steady rate of stretching applied across a canvas larger than anything a heartbeat was ever built to measure. That number isn't even fully settled, which is its own kind of strange. Measurements based on the afterglow of the Big Bang, the same cosmic microwave background responsible for the 630 kilometers a second measured earlier tonight, produce a Hubble constant close to 67. Measurements based on nearby exploding stars, called supernovae, used as reliable distance markers in the more local universe, consistently produce a noticeably higher number, closer to 73. The gap between those two values, small on paper, is large enough that professional cosmologists have spent the better part of a decade arguing over it without resolution, a disagreement serious enough to have earned its own name in the research literature. The Hubble tension. Nobody yet knows whether it points to a mistake buried somewhere in one of the two methods, or to something genuinely missing from the physics used to connect the early universe to the one we measure today. There is no comparing these two rhythms directly, and that mismatch is exactly the point. Your heartbeat measures time passing for a body small enough to fit in a chair. The Hubble constant measures space itself growing, continuously, without pause, across a canvas that makes the distance from your chair to the nearest star look like nothing at all. One clock ticks in a chest, the other doesn't tick at all. It simply stretches, invisibly, everywhere, all the time, including the empty air between your body and the nearest wall, by an amount too small in any ordinary room to ever measure directly. And yet both rhythms are running underneath you right now, in the same instant, at scales too different to ever be confused for one another, and too real to treat either one as more fundamental than the other. A heartbeat measuring a life, a constant measuring a universe, both keeping time in their own register, while you sit here listening to neither. In 1689, Isaac Newton described a simple experiment requiring nothing more than a bucket, some water, and a length of rope. Hang the bucket from a twisted rope, fill it with water, and let go. At first, the bucket spins while the water inside stays relatively still, its surface flat. Slowly, friction drags the water into spinning along with the bucket, and as it does, the water's surface curves upward at the edges, forming the familiar concave shape water takes on when it's rotating. Newton's actual question wasn't about the shape of the water. It was about what the water's motion was relative to. Early in the experiment, the bucket spins and the water doesn't, yet the water's surface stays flat. Later, the water spins along with the bucket, and the surface curves. If motion only ever meant motion relative to the bucket, this makes no sense. At both points, the water's motion relative to the bucket is different, but only the second stage produces the curve. Newton concluded that the water's curving surface must be responding to something other than the bucket, something he called absolute space itself, a fixed, immovable backdrop against which true rotation could be measured, independent of any other object nearby. Not every physicist accepted the conclusion, even at the time, and the objection only grew sharper centuries later. If there is no privileged frame for straight-line motion, as Einstein would later insist, why should rotation get to be different? Physicist Ernst Mach proposed, in the late 1800s, an alternative explanation entirely. The water's surface curves, not because of some abstract absolute space, but because of its motion relative to all the other matter in the universe combined, every distant star and galaxy contributing some vanishingly small share of the effect. Spin the bucket in a universe empty of everything else, Mach argued, and there would be nothing left for the water to be rotating relative to, and the curve, on his account, should disappear entirely. Nobody has ever built that experiment. Nobody could. Removing all other matter from the universe to test the idea isn't a matter of better funding or a more patient research team. It's a test that would require rebuilding the cosmos to specification first. What's left, more than 3 centuries after Newton first spun that bucket, is a question still without full agreement. Does rotation, unlike straight-line motion, get to answer to something absolute after all? Or is even a spinning bucket of water quietly measuring itself against every galaxy and every hidden supercluster counted so far tonight, using a connection too diffuse and too distant to ever measure directly? Physicists still work with both possibilities alive in the literature, 300 years on, and tonight isn't going to be the night that settles it. A dramatic, real-world version of the same puzzle appeared in Paris in 1851, when physicist Léon Foucault suspended a heavy pendulum from the dome of the Pantheon and let it swing freely for hours. The pendulum's swing plane appeared to slowly rotate over the course of the day, tracing a full circle in roughly 32 hours, even though nothing was pushing it sideways. The explanation is straightforward. The pendulum's swing plane wasn't rotating at all. The building, and the ground beneath it, and everyone watching, were rotating underneath the pendulum, carried by the planet's spin described at the very start of tonight, while the pendulum itself kept swinging in a fixed direction. It was, in effect, a bucket experiment built at the scale of an entire cathedral, and it settled, dramatically and publicly, that the Earth's rotation is measurable directly without reference to the sun, the stars, or anything outside the room. Seal yourself inside a windowless room with no way to look outside and check your surroundings. Sit a scale on the floor and stand on it. There are exactly 2 situations that would produce the identical reading, and no experiment performed entirely inside that room could tell you which one you were actually in. The first. The room is sitting still on the surface of a planet, held down by ordinary gravity, the same pull keeping your feet on the floor right now. The second. The room is out in deep space, far from any planet or star, being accelerated forward by a rocket engine at a rate that exactly matches that same planet's gravity. In both cases, the scale reads the same weight. Drop a ball in either room, and it falls toward the floor at the identical rate. There is no experiment, performed entirely inside a sealed room, capable of distinguishing held down by gravity from being pushed by acceleration. Einstein called this the equivalence principle and treated it as more than a curious coincidence. He built an entire theory of gravity around it, one published a decade after his original 1905 work on speed and simultaneity, general relativity, in which gravity isn't a force pulling objects toward each other so much as it is the curvature of space and time itself, bent by the presence of mass in a way that makes falling toward a planet and accelerating through empty space physically indistinguishable from the inside. Here's why this belongs in tonight's account rather than a separate one. Every motion counted so far. The planet's spin, the fall around the sun, the drift toward the Great Attractor involves acceleration of one kind or another, a change in speed or direction or both. None of it is the pure, unaccelerated, constant velocity motion that Einstein's original 1905 physics handles so cleanly, the kind where every observer gets equal claim to being still. Acceleration and gravity, tangled together by the equivalence principle, behave differently. And untangling exactly what still means for an accelerating, spinning, falling body turns out to be a genuinely harder problem than the one Einstein solved first. You have never once in your entire life experienced pure, unaccelerated motion. Every layer carrying you tonight, spinning, falling, orbiting, drifting, involves some acceleration folded in. That every inertial frame is equally valid was never quite the whole story for a body like yours. NASA's Gravity Probe B mission, launched in 2004, tested an even stranger prediction buried inside general relativity, that a large rotating mass, like the Earth, doesn't just bend space around it, it drags space itself around slightly as it spins, an effect called frame dragging. 4 ultra-precise gyroscopes kept spinning in orbit for over a year, drifted by a tiny, specific angle predicted almost exactly by Einstein's equations, confirming that the planet's own rotation subtly twists the fabric of space and time in its immediate neighborhood. Not just curves it, every physicist agrees on the measurement. The local group moves at roughly 630 kilometers a second, relative to the cosmic microwave background. What physicists do not fully agree on is what that measurement is allowed to mean. One camp treats the cosmic microwave background frame as nothing more than a convenient, practical choice. No different in kind from the local standard of rest described earlier, just vastly more useful because it happens to be visible from every point in the observable universe at once. On this view, calling it the closest thing to a true rest frame is a description of convenience, not a discovery about the deep structure of reality. Relativity's core claim that no inertial frame is privileged over any other remains fully intact. The cosmic microwave background frame is simply the one everyone finds easiest to agree on and measure against. A second camp takes the special status of that frame more seriously, pointing out that it isn't chosen the way the local standard of rest is chosen, by convention and averaging. It's fixed by the actual physical history of the universe itself. The moment matter and light decoupled roughly 380,000 years after the Big Bang, an event that only happened once, everywhere, leaving behind a genuinely unique frame in which that ancient light looks the same in every direction. On this view, the cosmic microwave background frame isn't merely convenient, it's meaningfully distinguished from every other possible frame by the actual history of the cosmos. In a way, the local standard of rest never was. Neither camp has produced an experiment capable of settling the disagreement, because the disagreement isn't really about a measurable fact. Both camps agree completely on the number, 630 kilometers a second, and on every prediction that number makes. What they disagree on is a question sitting one level above the physics. Whether being practically useful and being philosophically fundamental are the same thing, or two entirely different properties that happen, in this one case, to point at the same frame. Some cosmologists frame the disagreement in terms borrowed from philosophy of science rather than physics itself. The difference between an epistemically privileged frame, one simply easier for us to measure from, and an ontologically privileged frame, one that reflects something genuinely special about reality rather than about our vantage point within it. The cosmic microwave background is undeniably the first. Whether it also qualifies as the second remains the actual fault line running through the debate, one that shows no sign of resolving through better satellites alone, since both camps already accept the same data. A more precise measurement wouldn't settle which philosophy of measurement is correct. That disagreement is still open, published, argued over at conferences. Tonight's account isn't going to resolve it, because nobody currently alive has resolved it either. Set aside, for a moment, every argument about which frame deserves to be called fundamental. Return instead to the room you are actually sitting in, because every layer named tonight is still running underneath you, right now. The ground beneath you is still completing its daily turn, carrying you through roughly 40,000 kilometers of circumference every 24 hours. The planet is still falling around the sun, tracing a curve it will never retrace, at a speed that would carry you across an ocean in minutes. The sun is still dragging the entire solar system through a 230 million year lap around the galaxy's center, a lap barely begun 20 times since the sun itself formed. The galaxy is still sliding sideways, pulled by a hidden mass it cannot see directly, itself falling toward a supercluster whose boundary is still being mapped, and underneath all of it, the local group is still closing on the ancient light left over from the universe's first few 100,000 years. At 630 kilometers every second, a number 3 independent satellite missions have each confirmed. None of that has paused for this conversation. None of it required you to notice, to believe it, or to feel it at any point across the last several minutes. They run simultaneously, continuously, all through the ordinary evening you are having right now, exactly as they have run through every evening you have ever had, going back before you could form a single memory of any of them. Even the air moving in and out of your lungs right now is being carried along by every layer named tonight, at every one of tonight's speeds, without any of it disturbing a single breath. Blood is still circulating through your body at the ordinary, unhurried pace it always has, entirely unbothered by the fact that the room performing that circulation is itself falling, spinning, orbiting, and drifting, all at once, in directions that have nothing to do with each other. Think of it less like a single note repeating and more like a chord. Several distinct notes sounding together, none of them silencing the others, none of them waiting their turn. The spin is one note, the fall around the sun is another, the drift toward the ancient light is a third, sounding underneath the first 2 the entire time. You have never once heard only one note of that chord in isolation. You have only ever heard, or rather lived inside, all of them sounding together, for every second you have been alive. Here's the part worth sitting with, quietly. Before we finish counting, you asked, at the very beginning of tonight, which of these numbers was your real speed? That question assumed the layers were competing, that only one of them could be telling the truth about you at once. They were never competing. Every single one of them has been true simultaneously for your entire life, without needing to cancel any of the others out. There isn't a clean analogy waiting to make this feel simpler. So, here it is directly, without one. How fast are you really moving? Was never a question with a single correct number underneath it, hidden and waiting for a good enough telescope, a patient enough physicist, or a sufficiently advanced instrument to finally uncover. It was a question built on an assumption that turned out to be false the moment you started checking it seriously. The assumption that speed is a property an object has on its own, the way mass or shape might be, rather than a property that only exists in relationship between one thing and another thing chosen to measure it against. Every number counted tonight was accurate. All of them, at once, without contradiction, 1,670 kilometers an hour relative to the planet's core, 107,000 relative to the Sunday, 828,000 relative to the galaxy's center, 630 kilometers a second relative to the oldest light in the universe. None of those numbers was competing with the others for the title of real. Each one was answering a different question, honestly, and the question itself real speed, was the part that never quite made sense once you looked closely enough at what speed actually is. Stillness works the same way, which is the part most people never sit with long enough to notice. Being still was never the absence of motion. It was only ever the state of not changing position relative to whatever you happen to be comparing yourself to. You are still relative to this room. You are not still relative to the Sunday. You are not still relative to the galaxy's center, or the Great Attractor, or the ancient light filling every direction you could point a telescope. All of those are true simultaneously, and none of them cancels any other one out. It would be tempting to reach for weightlessness as an exception, the closest thing to genuine stillness a person could actually feel. An astronaut floating inside an orbiting station feels no scale pressing up against their feet, no sensation of falling or spinning at all. But weightlessness isn't stillness either. It's the same trick from early in tonight's account, played out in orbit. The astronaut and the station are falling around the Earth together, at the same rate, which erases the sensation of falling without erasing the fall itself. The astronaut is moving at close to 28,000 kilometers an hour relative to the ground below. They simply share that speed completely with everything around them, which is the entire, ordinary trick stillness has always relied on. At any scale, in any room, on any floor, there is no version of you, and no version of this room, holding still against some final, absolute backdrop the universe keeps in reserve. There is only ever this, still, relative to something, moving, relative to something else, both, always, at the same time. None of tonight's account is confined to physics journals and thought experiments. One piece of it sits quietly inside a piece of equipment most people carry in a pocket every day. GPS satellites orbit roughly 20,000 kilometers above the surface, moving at close to 14,000 kilometers an hour relative to the ground, and sitting in a noticeably weaker gravitational field than anything on the surface experiences. Both of those facts affect the satellite's onboard atomic clocks, and they affect them in opposite directions. Relative motion, the same effect measured by Hafele and Keating's flying clocks, makes the satellite clocks run slightly slower than identical clocks on the ground. Weaker gravity, a separate consequence of general relativity, makes the satellite clocks run slightly faster. Add both effects together, and the satellite clocks end up gaining roughly 38 microseconds every single day compared to a clock sitting still on Earth's surface. 38 microseconds sounds too small to matter until you multiply it by the speed of light, which is exactly what a GPS calculation does. Left uncorrected, that tiny daily drift would accumulate into a position error of roughly 10 kilometers within 24 hours. An error large enough to place a car on the wrong street, a ship in the wrong channel, or a rescue team at the wrong coordinates entirely. Every GPS satellite carries clocks deliberately adjusted before launch, tuned to run at a slightly different rate than an identical clock on the ground, specifically to cancel out an error that exists only because relativity is real and measurable, not theoretical. When GPS was first being designed in the late 1970s, not every engineer on the project was convinced the relativistic correction was actually necessary. The effect seemed almost too small and too strange to trust. Rather than argue about it indefinitely, the team built the first satellite with a switch, allowing the relativistic clock adjustment to be turned on or off after launch. Once the satellite reached orbit, they left the correction switched off briefly to check. Position errors began accumulating almost immediately, exactly matching the size and direction relativity predicted. The switch was turned on within days, and every GPS satellite launch since has carried the correction from the moment it reached orbit, no longer treated as a theoretical nicety, but as a basic requirement for the system to function at all. There is exactly one reason this deserves a closer look. Nothing described tonight, the planet's spin, the fall around the sun, the 630 kilometers a second against the ancient light, the fact that speed itself has no universal reference point is confined to telescopes, satellites, and physics papers written for other physicists. A piece of it rides in your pocket, correcting your position on a map every single time you check one, whether or not you have ever once thought about why or noticed the quiet debt it's settling on your behalf. Go back to the very first sentence of tonight, the one that told you nothing in this room was actually still, that the walls and the floor and the air inside it were already moving faster than any jet in the sky. That sentence was true and false at exactly the same time, in exactly the way every sentence about speed turns out to be. The room was sitting still. Relative to you, you were not sitting still. Relative to the planet's core, the sun, the galaxy, the Great Attractor, or the oldest light in the universe. Neither claim cancelled the other. Both were simply answering a different question. The way I'm sitting down and I'm hurtling through the galaxy can both be true statements about the identical body, in the identical chair, at the identical moment. There was never a hidden number waiting underneath all the others. A true velocity the universe was keeping to itself until someone built a good enough instrument to finally read it off. Not because the search failed. Because the thing being searched for was never the kind of thing that could exist. Speed isn't a possession an object carries around the way it carries mass or shape. It's a relationship, drawn between two things. And it only ever answers the question you specifically asked it. Relative to what? Which means the real answer to tonight's opening question was never a number at all. It was a correction to the question itself. You do not have one true speed through the universe. You have exactly as many speeds as there are things to compare yourself against. All of them equally real, none of them cancelling any other, for as long as any of those things exist to be compared against. 5 centuries ago, Copernicus removed the Earth from the center of the universe, and it took the culture built around that older, comforting model more than a century to fully accept the demotion. Tonight's account asks for something quieter, but, in its own way, stranger still. It isn't asking you to accept that some other object, the sun, the galaxy's center, the cosmic microwave background, deserves the center instead. It's asking you to accept that the very idea of a center, a fixed point everything else could be measured against, was never available to begin with, for the Earth, the sun, or anything else that has ever existed. Copernicus moved the center. Tonight removed it. That is a harder demotion to fully feel, because it doesn't offer a replacement to hold on to. There is no new true center to relocate your attention toward, only the quiet, repeated confirmation that the search for one was always going to come up empty, no matter how far the instruments improved. Being still was never a place you could stand. It was only ever an agreement. Quiet and local, between you and whatever you happen to be measuring yourself against. Tonight, in this room, in this chair, in this one small, moving corner of everything. Every motion counted tonight began before you had any way to notice it, and none of them has paused since. Not for a single second, not even the ones spent asleep. You were spinning with the planet's rotation before you took your first breath. You were falling around the sun before you had a name. You were being carried through the galaxy's slow 230 million year orbit, wobbling gently above and below its disk, before anyone who knew you was even born themselves. You were drifting toward a hidden mass no telescope has ever directly seen, closing on the oldest light in the universe at 630 kilometers a second, before the words Great Attractor or cosmic microwave background had been written down by anyone. None of that motion asked your permission then or now. None of it will ask your permission tomorrow, or on any night after this one. It simply continues, layer folded over layer, exactly as it has for every quiet, unremarkable evening of your entire life, whether or not you were awake enough to remember thinking about it. So the room around you tonight is not an exception to any of this. It's simply where all of it happens to be passing through, right now, on its way to wherever the next layer is taking it. The walls hold still around you because they are moving at exactly your speed. The floor holds still beneath you for the same reason. Even the phrase "every direction at once" is not exaggeration once you count the layers honestly. The spin carries you one way. The fall around the sun carries you another. The galaxy's orbit points a third way entirely, and the drift toward the ancient light points differently still, each vector answering to its own separate cause. None of them cancelling the others, all of them summing into a single, complicated, ever-shifting motion no one has ever stood still long enough, from the outside, to fully measure. Whoever eventually listens to these same words after tonight will be sitting inside the identical arrangement, still spinning with a ground that has shifted slightly beneath them, still falling around a sun that has aged by exactly the amount of time separating their evening from yours, still carried through a galactic orbit too slow to notice the difference. The layers do not expire. They do not belong more to tonight than to any other night. They are simply what a body sitting inside a universe like this one has always been doing, quietly, underneath every ordinary evening anyone has ever spent doing nothing in particular, tonight included. And somewhere underneath all of that shared, borrowed stillness, the same restless universe that has been carrying you since before you could ask it a single question is still carrying you now, quietly, toward tomorrow, at every one of tonight's speeds, all at once, without contradiction. We've drifted tonight through a room that never once stopped spinning, a sky that quietly changes which star gets to call itself north, and a hidden mass strong enough to pull an entire galaxy sideways without ever once being seen directly. We've wandered from a bucket of water spun 3 centuries ago to the oldest light in the universe, and found, at the end of all of it, that the two were asking the same question the whole time. Nothing in this room was ever actually still, not at the very start of tonight and not now. The walls and the floor and the air inside it already moving faster than any jet in the sky. That was the first thing you were told. It's still true. In exactly the layered, complicated way it was always going to turn out to be true, and by now, that complexity should feel less like a trick and more like an old, familiar shape finally coming into focus. None of those layers were ever separate from you. The spin, the fall, the drift, the ancient light closing in at 630 kilometers a second. All of it running through the exact room you're sitting in. All of it as much yours as it is the universe's. Because there was never a meaningful line between the two to begin with. Our was always the more accurate word. Not because the universe is friendly, or watching, or waiting for you specifically. Because you are built from the same motion as everything else counted tonight, carried by the same layers, answering to the same quiet absence of any final, fixed ground. If your eyes feel heavy, let them close. You don't need to hold on to a single number from tonight to keep drifting through all of them regardless. The spin doesn't need your attention to continue. Neither does the fall, or the orbit, or the drift toward a mass you'll never see. Sleep, and every layer keeps running exactly as it was. If this felt like home, leave a comment when you wake up. Tell us which layer surprised you most, or which one you already knew and finally heard explained properly. If you're still here, still listening, the next chapter is waiting whenever you're ready for it. Dozing off tonight isn't a failure of anything. It was always the point. The universe will still be here when you wake up. So will we. Good night.